Be very judicious about where we go with this today because of our time constraints. Also, forgive me if I'm a bit tired. I was up until the ridiculous hours of the morning trying to order a Nintendo Switch 2. So, I don't know why. I don't know why sites like Target and Best Buy can't make sites that work, but Walmart can. So kudos to the devs at Walmart, I guess. All I can say is that the students who built this were probably not my students, so.
You just can't handle the Nintendo traffic.
Yeah, any pre-order traffic. It's always a mess for a pre-order for that kind of stuff. So, all right. VE was the runtime of Dijkstra's algorithm. So very briefly, because this is not going to be on the exam. Also, I don't know where the exam is. Professor Fiore is busy trying to figure that out because we should have gotten notification from the dean's office, but I will send you information. I will send you updates about where the exam is. If it's not going to be taken if it's not going to be taken all together with everybody else, then it will be taken still at that same 3:30 time slot that I was talking about in this room, right? But otherwise, it should be in like a big lecture hall. All right, Dijkstra's algorithm. V is the number of vertices. E is the number of edges. What is the running time of Dijkstra's algorithm BIGO notation? There's lots of different runtimes for Dijkstra's algorithm. In fact, we can check Dijkstra's algorithm and see. And you'll see that there's a lot that, let's see. Worst case performance is O of E V log V. The idea here is, though, the Dijkstra's original algorithm ran for v squared time. This is because the idea here is that for each node, what you have to do is you have to check, for every node, you check it, you have to go and figure out which is the node with the lowest cost, and figure that out, and then update for your edges. The maximum amount of edges you have, by the way, is equal to your vertices squared. Think about that for a second in a simple graph. Maximum number of edges is vertices squared because adjacency matrix is a matrix that's square, and the maximum amount of edges you can have is every single one of those entries filled. So, but the reason why this is not the runtime is because we were just simply going through and naively looking at the smallest one, right? For Dijkstra's, and this is relevant for 3223. The best case scenario, a better way of doing this is by using a heap-based priority queue. They use something called a Fibonacci heap. You could use a binary heap, but a Fibonacci heap works pretty well. Okay. But basically, for each node, you have to check all the other kind of possible connections it has. So. Now, with this one, two of the most common divide and conquer sorting algorithms are Quicksort and merge sort. In practice, Quicksort is used for sorting data in main storage rather than merge sort. What is main storage? Your RAM. That's your RAM. So Quicksort is used for doing that in memory rather than merge sort. So Quicksort, why is this the case? Quicksort, might be a bit more, you can do Quicksort in place. That's pretty much the reason. Merge sort, you could ostensibly do it in place if you had linked lists, but then you have all the overhead of memory of those memory pointers and stuff. Quicksort can be done in place. Merge sort, I've always seen that. How do you do in place merge sort? That's left as an exercise. No, I don't. It's a mess. So you can't really do it like that. So why is Quicksort the preferred sorting algorithm? You can do it in place and you can do it quite easily. And it's quite memory efficient to do it in place, even though it's recursive. Another reason, though, for the opposite, why would you want to use merge sort on, why could you do merge sort on, stuff stored in actual storage, right, your hard disk space? And the answer is that merge sort, right, you can create you can make one big sorted block, you can make another big sorted block, and then you can merge them, right? You can take those separate answers and merge them. So you can work on multiple different sorted things and then merge them if you have to. Merge sort is actually the way that you would handle if you had multiple processors to You'd use whatever sorting algorithm you want on a bunch of different groups of numbers to sort them. If you had if you were in a distributed computation kind of scenario, and you could just then call merge to merge those separate answers in O of sub n time. All right. Merge sort's worst case runtime is O of n squared, but as expected, a runtime of n log n if the partition function works well. What needs to be true about the partition function in order for the runtime to be n log n? Okay. So what do we assume about so the answer to this, or the hint for this, is that it's very similar to the same assumption we have to make for a binary search tree that doesn't self-balance, right? What is that assumption for the partition algorithm? What? Yes?
That has to choose like the middle number?
Yeah, that's going to choose the median number here, so that you're going to end up with half the stuff on one side of the partition and half the stuff on the other side of the partition. Specifically, I think it's got to be like at least 75% split, but it's got to be some kind of split where it's reasonable and you're not just simply, because the worst case runtime is you choose like the first item, and then the second item, and then the third item as your pivot, and then the fourth item, and so everything ends up to the right or to the left. And in practice, how can we ensure this happens? And the answer is you can always get really, really unlucky, but you can do a couple things. First, there's the dual pivot method that Java actually uses, choosing two pivots, which changes up the algorithm. Another way you can do that is discussed in the textbook and in the slides, is that you can select multiple numbers, like the first, the last, and the middle, because you can do that in constant time. Figure out which of those is the middle, because that one is more likely to be a median value, and then do that. And that just improves your odds of getting a number that is going to be less wasteful. Okay. You can play this with this one around later, but this is pretty much the end of this exam that I wanted to go over. The Bridge of Königsberg. This is basically one of the birthplaces of graph theory. The puzzle is solvable now due to the results of World War II destroying most of the bridges. So, but the idea here is that could you have these land masses? Can you travel across each of the bridges only once? And the answer is no, and Euler proved that you could not using math, which was very unsatisfying to children, I guess. All right. Where is my other? Come on. Nope. Okay. I could have sworn I had. Oh, right, because I didn't have GitHub open here. Here we go. So let's look at Harvard's practice final exam. Some of these are from, so this is what I'm saying, like some of these, so you saw one exam that I said, okay, some of these questions are more from an algorithms class where it dips at the beginning of an algorithm. Here we have something that dips into the beginning of object-oriented programming and then goes into algorithms. It really depends on the speed of the classes. Most classes, very quickly, most schools either do a 4-sequence or a 3-sequence for their programming classes. We used to do a 3-sequence, and we felt the attrition rate was a bit too high from that. So now we do a 4-sequence, where it's intro, objects, data structures, algorithms, essentially. Algorithms are also, that's kind of the computer science, the entire point of a computer science curriculum, in my opinion, is for computer scientists, is get you into the into the algorithms course, where you have to be hazed by a lot of math. And if you don't like that, then you go to IST and just deal with practical stuff and make tons of money without having to deal with any of that math. It's all the same.
It's all right. You still struggle with a little bit of math, though.
You do, but you don't have to do annoying proofs about recursive stuff. Okay.
No, you just got to turn it on and off and hope.
So you can see here that we've got object-oriented programming, some basic questions, a recursive function here. Well, let's take a look at that quick recursive function. Given this function, whoops. Consider the following recursive methods. Static mystery int n. If n is less than or equal to 1, return 1. Else return 2 times mystery of n of 1. What's returned by the call of mystery 3? Mystery 3, yeah, it's not no value, I bet. It would be, so if we have 3, that's going to be return 2 times mystery 2. Let's call it M2. M2 is going to be 2 times M1, and this is kind of the way I would do writing out these kind of things. Basically, you figure out what these calls would be, and then you can always do it into a more formulaic thing if it's too big. And M1, well, if n is less than or equal to 1, it's 1, so this entire thing is 1, so it's 2 times 1, so this thing is 2, so it's 2 times 2, which is 4. All right. With a poorly chosen hash function, it's possible to have a situation in which the search time of a hash table of n items goes to, and this is where big O, where we're looking for the most correct answer. Because technically you could say, yes, it's definitely never, remember, big O means it's never going to be worse. So I can say, yes, the hash function is definitely never going to be worse than n factorial. But that's not the most accurate answer, right? That is a useless answer here, okay? So a hash function, has been my example of a terribly chosen hash function? H of x is equal to 0. That's a terribly chosen hash function. Everything goes to index 0. So in that case, what is the expected time to add and remove an item, right? O of n, exactly, because it's just essentially a list with a lot of extra steps. All right, this one's a fun one. A binary tree is constructed of nodes that have of the following class. N, so we've got this public stack. So we've got a node here. Notice they focused on not learning generics. It's fine. But I like the fact that I teach generics. I really like it. I'm attached to it as a concept. Public static node mystery root. If root.write is equal to a null, then return root. Otherwise, return mystery to the right. Right? So if you have something go right, do mystery write. Otherwise, do root. So you consult 3 supposedly tech-savvy consultants, and you get the following 3 opinions about what the method does when passed a reference to the root node of a binary tree. It returns the last node visited in order, it returns the last node visited in a post order, and it returns the last node visited by level order. Okay? Level order being basically the heap order, right? It being the breadth first search. That's what level order is. Okay? Make sense? It's the order in which you would label stuff in a heap. Okay, so which of these opinions are correct, regardless of what the tree is? Which ones are correct no matter what? Okay, so we are just going to do. So, right, there's our function. Last node visited by in-order traversal. So here we go. So suppose we've got a tree over here, right? So let's figure out what this mystery function does, okay? We've got some node, and then we've got our subtrees, right? Okay. So what mystery does is says if the root is not equal to null, so if the root is null, then return it. Otherwise, if it's not null, go to the right. Return mystery.write. So this is going to return mystery.write, which is going to call mystery.write, which is going to call mystery.write. It's going to keep going right until it gets to effectively the rightmost node, right? It's going to find this node over here. So it returns, so in a binary search tree, that would be the biggest item. It's also the rightmost item. Okay, let's assume that it is a binary search tree. It is not, but, so let's see. It returns the last node visited in an in-order traversal. So in an in-order traversal, right, that says, let's do all the stuff to my left first, then myself, then all the stuff to my right, recursively, right? In order on the left, myself, in order on the right. So in an in-order traversal, the thing furthest to the right is going to be the last thing. Make sense? So opinion 1, that is correct. Last thing in a post-order traversal. Post-order traversal says do left, then right, then myself. The only way that this is the only way that the rightmost node ends up being the last thing. Sorry, the only way this returns to the rightmost node is if that's the root, but it says regardless, right? So on this situation where it's over here, right? Again, we'd be going right, and it would not be the last node returned by post order. The last node would be the first one. So no. Okay. last node by a level order traversal. And I'll just quickly do a counterexample. Okay. This is the rightmost node over here. Level order traversal. 1, 2, 3, 4, 5. Right? That's level order traversal. It's breadth first search. Okay? It's not a term we really learned, but it's easy enough to introduce here. It's not also one that I'll use on the exam. I'll use breadth first search on a graph problem, but never use. So that doesn't work. So only one. This is one of my favorite problems on this exam. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets. So it can be determined very quickly whether or not a given license plate number is in the database. Speed of response is important. Efficient memory of use is also important, but not as important as speed. Which of the following data structures would be most appropriate for this task, right? We are storing essentially 1,800 numbers, okay? We're storing 1,800 numbers. We need to make sure that it's quick and memory efficient, but prioritize quick. A sorted linked list. So how do you check if something's in a sorted linked list? You have to iterate. In a sorted linked list, you have to iterate through the entire thing. There's no getting into the middle of a linked list automatically. So that's going to take O of n to search, which is not a great time for that one. A sorted array with 1,800 entries. Now we're getting somewhere, right? How do you find something in a sorted array? You find it by doing binary search, right? Search on, choose the middle number. If the number you're looking for is less than or greater than, go left or right, respectively. Otherwise, you found the number, or if you found the number, return that, right? If you found the number, return that. Otherwise, go left or right, respectively. This is actually our most memory efficient answer. So if we were going for memory efficient, this is the one to go because arrays don't require any extra overhead. And this would take O of log n time, right? Okay, balanced binary search tree. I'm just trying to go fast here as opposed to write anything. A balanced search tree. Balanced search tree would take log n time to find something in a balanced search tree because you go left or right. That discards half your search space, so you keep having it, and so that would be log n time. That takes about O of n overhead though, so it would take extra space. So the balanced binary search tree, the sorted array is still in the lead. Now we've got two interesting things here. A hash table using open addressing with 1,800 entries and a hash table with 3,600. I like when it used to be 3,600 and 10,000. So a hash table with 1,800 entries, right? I assume that means it has the capacity of 1,800. In which case, right, you're getting actually O of n time and O of n time because you're close to your capacity. You're close to your maximum amount of lookup time, right? On the other hand, here it would be a constant time with O of n space used. Okay, and there's a formula that we can use by Knuth's formula. Knuth hash table lookup. Expected lookup. I think I know it off the top of my head, but I do want to make sure that I know. Yep, here we go. Linear probing. Okay, yep, there we go. The assumption is here we go. The assumption is O of n, 1, that's a lot of numbers, so I'm going to translate that, okay? Okay, the expected lookup is, so this is the expected lookup in a hash table, how fast that goes. The expected number of lookups you have to make is 1 plus 1 over and this is an alpha, so we're already getting into the Greek, but I'm going to make sure that we understand what that is, right, in a second. And this is using linear probing, not chaining, okay? And I believe that was, that was 1 minus the load factor. There we go. So the load factor is basically the limit at which, once you hit it, that is the point you're going to say, I am rehashing this thing. I'm going to be splitting it up. So in in something that is 50%, right, where we set the load factor to be 50%, right, over here, 0.5, let's do the math very quickly. Okay, so if you're looking at 50% load factor, then our expected lookup time is 1 plus 1, what's 1 minus 1/2? That's 1/2. So we've got 1 over 1/2. 1 over 1/2, that flips it. That turns this entire thing into 2. So if we have a load factor of 50%, if we set our load factor of 50%, our expected lookup time is 3 lookups. Let's go ahead and now examine that for something where it's like 90% of the way full. 1 plus 1 over, okay, 1 minus 90% of the way would be 9/10, right? That becomes 1 over 10, which becomes 10, which means we would expect to do 11 lookups, right? So having more entries, so having more open entries with linear probing allows us to do this lookup a lot quicker. Okay, so the formula there is, again, I don't know if it's necessarily bit. I don't think it should be O. I think is it O or is it E, right? And the expected cost for a successful lookup is this. Unsuccessful insertion, expected cost of an insertion is this. So regardless, you've got the formula now. Okay. But you don't necessarily need that formula for the exam. That's not one, I just, for completeness' sake, that's why you need this, because this one is basically approaching that when you say you have 1,800 entries, which is the amount we are adding, we're getting something that looks like this, which you might recognize being a bad idea. Okay. We did this on our exam, so on our first exam, so no, we don't need that. All right. In which of the following implementations could a data dictionary of n items could at least in some cases require O of n operations to search for an item? I haven't seen this one before as a practice question, but let's go ahead and if n was small, sure, you could get issues like this, but so first off, a 2-3 tree is a special tree that basically means you can have 2 or 3 children. It is one of the forms of a self-balancing tree. So I see where he's going with this. Okay, 2-3 tree. This is it's a self-balancing tree. This is always going to be log n. Okay. A binary search tree, we've seen that could be O of n time in the case where we have a terrible implementation, where it's just not a balanced tree, right? Where basically we have a linked list with extra steps, as I call it. So this could require O of n operation. And a hash table, we just established when your load factor is terrible or your hash function is terrible, then it could be O of n time for a lookup. It's very rare. Make sense? So, Huffman trees. Which of the so let's see. A Huffman tree this is honestly a great question. I wish I had thought of it for putting on my exam. A Huffman tree is constructed for a text document using 5 characters. The character E appears the most frequently, and the character I has the next highest frequency. Which could be, of the following could be the Huffman tree for this document? 1, 2, or 3. Why am I ruling out this first one without even why am I just throwing that first one out for a Huffman tree? It's not this. Yeah, the I, what was that? Yeah? No, not 2 children, yes.
There's ambiguity, because then I is 0, is just 1, and then T is 1, 0.
Yes. So the ambiguity is the result of why we enforce a rule that all endpoints in a Huffman tree for letters or characters have to be on leaves, right? All characters have to be on leaves for a Huffman tree because there could be ambiguity otherwise. There would be ambiguity otherwise. So there we go for 2 and 3. Now, we're going to rule out 3 as well very quickly, okay? And the reason is because the most common character is E. So that means it should have the shortest distance from the root. Okay. Next, the most common character, following most common character is I. So the question is it 2 or none of these? Now, E, this is the most common character. What about this case? Can we reasonably create a scenario where we get this structure? And the answer is if T and O, right, they combine and maybe they have a weight of, let's do some quick thing here, 3, and then we would need to do, let's see, actually maybe they have a weight of 4 or so, and then this has a weight of 2 and 3. These get added together into 5. Yeah, and then this has a weight of whatever. Wait, no, not 2 million. No, that won't work. That won't work. That would end up on the left. 4, 5, and this would have a weight combined of, let's say, 9. And so, yeah, I just need something bigger than 3, so 8 would be there, and that would work. So, yeah, if I is the next most common character, it makes sense for it to be the rightmost there. We could come up with a reasonable scenario for this. All right. The following array is to be sorted in ascending order. What algorithm will cause the array to be sorted as an intermediate stage in the sorting process? Okay. So let's see, bubble sort. Bubble sort will always move the biggest items to the top, bigger items to the top. For this one, bubble sort, no, because 52 should not end up in that spot, right? For heapify, I don't really see this necessarily because you're going to go through your array and you're trying to construct this doesn't resemble a heap, really, right? This doesn't resemble a heap. Insertion sort, no. Let's see. I'm trying to figure this one out. Quicksort doesn't make sense because you've got a pivot of 30. It says the initial pivot is 33. And if the initial pivot is 33, whoops. I'm really trying to look at this one. Initial pivot is 33. But if our pivot is 30, interesting line stroke there. If our initial pivot is 33, right, then we'd want some level of partitioning to take effect, right? Typically your partition is over there, or if it's linked list, then we'd be putting stuff that was less to left, greater to the right. So I don't see it being quicksort. Selection sort, with selection sort, assume we're selecting the biggest number for a sec. That does make sense for that to be here. For bubble sort. So, okay. But at the same time, how would this 74 get there? 74 we'd find the biggest item, and then we'd swap with 52. I don't see that necessarily happening. So let's just double check insertion sort for a second. 25, 47, 14 would push down there, 33 would push down to between those. The 52 would just no. So insertion sort, we know it can't be insertion sort. We know it can't be quicksort. Selection sort doesn't really make sense in this context because even though we are selecting it, right, for the biggest, why would that, the only thing that should swap would be 74 and 52, right? Because with the selection sort, the idea is you minimize the number of exchanges. And then the next thing would be 52 would get swapped over here. Or 52 would be found to be there and there'd be no need to swap. So I don't see being selection sort. I don't see being quicksort. So we need to re-examine our priors. Okay, what about bubble sort? Bubble sort would be 25, 47, 47 would swap with 14, 47 and 13 would then swap, 47 and 15 would then swap. So if it was bubble sort would have, the 47 would have moved higher. So the only thing I can think about is heap sort, and let's go ahead and just run through the heapify algorithm for a second. 25, so we have 25, 47, 14, 33, 15, 74, because now the only thing I can think of is he doing heapify in an interesting manner. So with heapify, we're going to work from back. 52, 74, 15, try to push this down. You can't push these down because they're already a bedrock, so to speak. 14 swap with 74. Ooh, yes, this does work. Okay, 14 swaps with 74. And then 47 swaps with 3. Okay. And then 3 swaps with 25.
Oh, that's supposed to be
33? Ah, okay. Now, the reason that this could potentially work, even though 74 is beyond there, and I can see this, is because this actually does work as a heap. I forgot about that. Because if you're in the intermediate state of heap sort, right, then 74 will end up as, we make a max heap, right? 74, we end up with 74, and then we have the sub heap over here, and we have the sub heap over here. But what do we need to do heap sort? We remove the top element, and then we move it over here in the back as kind of our last, and we kind of pretend it doesn't exist anymore. Okay, so let's pretend 74 doesn't exist anymore. Ask ourselves, is the remaining bit a max heap? And the answer is yes. 52 has these two people as children. Okay, 47 has these two as children, and 25 has these as children. That is a child. It works. I can draw it out for you. 52, 47, 25, 33, 15, and 14, right? Ignore the fact that 74 exists because that's part of the sorting algorithm. This works as a heap sort. Okay. Right? Always reestablish. It's always worth to go back. I'm not perfect either. Like I said, I'm running on ridiculously low hours of sleep because darn you, Nintendo. All right.
Wait, because you did for the pre-sale?
Yeah, I got the pre-sale. Okay. All right, so let's go ahead and I want to do, let's see. I'm just trying to go and make sure because I haven't done a lot of coding yet, so I want to try to hit some of the coding questions here. That would be good. No, I want to make sure I want to hit this one, the hashing question, okay? So this is a question that will be a question of this kind will be on the exam, okay? So you're given a hashing table of size 7 that uses open addressing, okay? And in these, we assume we're not going to rehash, okay? The following sequence of keys are to be inserted: 5, 17, 8, 23, 3, and 5. Insert the keys using each of the following approaches. If overflow occurs, say so and indicate the element that causes the overflow. In other words, if we get a collision, let me know and tell me why are we getting a collision. So we are going to, I am like, why am I not screenshotting? Because I'm hitting the function key, not the window key. Okay, so we're going to grab these because we're only going to need to answer A and B as opposed to the other ones. 100, and we are going to paste these, and we are going to okay. Oh, and I suppose I should grab the numbers that I need for the problem. Okay. So this question is actually basically testing two things. Can you do modular arithmetic? What in the world? Come on. Go home, Microsoft. You're drunk. All right, we are going to go ahead and, how do I move this thing? Okay. No, I don't. There we go.
When you got work in the morning.
Yeah, apparently Microsoft must be needing a lot of coffee to this morning too. Okay, so this is our hash table. We need to insert these things in order. Okay, so our first thing is both of these use the hash function of x mod 7. And then how do we resolve it? So 15, what is 15 mod 7? 15 mod 7, let's see. So 15, the closest multiple of 7 is 14. So one beyond that is 15. So 15 mod, so if you think about it for 7, 15 divided by 7, that leaves me with remainder 1. So 15 is going to go over here. Let me go ahead and get 15. Okay, next we have 17. Well, 15 is 1, 15 is 1, 16, 17. Don't be afraid to use your fingers, right? So that would be 3, right? And you can double check that answer by saying, 17 minus 14 is 3. Okay, next, 8. 8 mod 7, that's a bit easier to figure out because we can just subtract. So 8 minus 7 is 1. So we want to put that here, but that's taken. So how do we resolve a collision in linear probing? We look for the next available slot. So I'm just going to do that with the drawing over here and say, hey, 8 goes there. We tried to put it there, but we couldn't. So 8 goes in here. Okay. I don't know if that's the most intuitive way to do that, but to draw that, but whatever, it will make sense. 23. So 23 is close to 21. 23 minus 21. Why 21? It's a multiple of 7. 23 minus 21 is 2. So we want to put it into index. We want to put 23 here. We can't because that's taken. We can't go there because that's taken, right? We look for the next available spot where next is defined by literally looking next to next to next to next to next, one at a time. So can't go here, can't go here. Aha, we'll go here. So 23. 3 mod 7, yes.
Sorry, on the exam, will you want us to draw the arrows?
On the exam, I think I just care about getting into the slot, not showing where the collisions occur. I care about the about where did things end up, not how did they get there. Okay, 23. So 3 mod 7 is 3. So we're trying to go to index 3, but we can't. So we end up looking for the next one. And then 5 mod 7, we're trying to go into here, but we can't, so we end up in index 6. All right. Now, assume for the sake of argument we had one more thing to add, and it was going to end up like maybe we're going to also add a 4. Where would the 4 end up? Nope, we would just simply go around for the next available slot. 4 would go over here. So because we have a slot available. We would just simply use modular arithmetic in our algorithm to do that. Now, quadratic probing, same kind of deal. 15, we can reuse our first answer. 15 and 17 go into these slots. Okay? 8 mod 7, we try to go into index 1, right over here. Right? 8 mod 7, we try to go into index 1. We can't, so we look for the next available spot, where next is defined by, instead of going, right, linear isn't just simply adding 1. What linear is saying is look 1 away, then 2 away, then 3 away. Here we're going to say look 1 squared away, then 2 squared away, then 3 squared away, then 4 squared away, from the initial spot. Okay? I suppose you could have a theme where you look 1 squared away from the spot, and then 2 squared away from the spot you just looked at for a total of 5, then 3 squared away for a total of 14, but no. So let's look at 8. 8 tried to go here, it cannot. 8 tried to go here, it cannot, so where's 8 going to go? It's going to look 1 squared away. So far, very similar. 23 is going to try to go here. 23 cannot. go into there, right? So we looked 1 squared away. Now we need to look 2. Now we need to look 2 squared away. So 1. So we were at 2. So 1, 2, 3, 4, 6. Right? 1 squared away, 2, 3, 4. So now we are going to put 23 over here as opposed to here. Why? Because we looked 1 squared away for this. This was 1 squared away. And now this is 2 squared away. Make sense? Quadratic probing just simply leaves bigger gaps as a result. Now we try to insert into 3. Now here's the interesting thing. We try to put 3 into here, and we end up with this, right? We tried to put 3 into slot 3. We get 1 collision. And then we try to put 5 into slot 5, and we're able to do that directly because what happens is we leave bigger gaps. The reason why you might use quadratic probing is that if you're getting if you're expecting these collisions, you're going to be getting less of them. But to calculate for quadratic probing, to calculate the next index, you're just doing continual additions. For this, you have to do a multiplication operation and an addition operation, so that can be a bit more expensive. But at that point, we are really thinking about, you're getting to really heavy stuff if you're thinking about that level of computational efficiency. Yes?
So, did we find that 23 leaves all the way to 6 again?
So this basically says, look 1 away, then 2 away, then 3 away, then 4 away for the next available slot. This one says, look 1 squared away, then if my spot is taken, if the spot I'm supposed to go in is taken, look 1 squared away from that my designated spot. If that's taken, then look 2 squared away from my designated spot. Then look 3 squared away. So we looked, so 23 was trying to go into here. It couldn't, so it looked 1 squared away, which would have been over here, right, which is a total of 1. Couldn't go there because that was taken, so we're going to look 2 squared away from my initial spot. 1, 2, 3, 4. So it goes 1, 4, 9, and it wraps around if need be. The other question involves using a resolution we didn't learn, which is double hashing, which is just simply if the first one doesn't work, try the second one, the first hash function. Okay. Let's see. I'm just double checking these functions and stuff. Okay. Boring, but okay. So this one is, I hate doing this one, but it beats having to make one myself, which is, all right, perform a depth first. So these are questions about doing depth first search and breadth first search. Always, also going to be on any data structures exam where you're first being introduced to graphs. And it's saying to start at vertex C over here. Cool. We're starting over here at vertex C. Okay. Select the smallest. So with depth first search, typically we need to have some kind of way of breaking ties because you have all these choices. How's the computer going to select them? Computer's just going to simply have a adjacency list or adjacency matrix of some kind, and we'll figure that out on its own. But on paper, we have to have a way so I don't have to deal with a million different solutions of the same problem. So I typically, when I write these problems, say break ties alphabetically. Here, though, for this problem, it's saying select the smallest edge first when appropriate. So we break ties by selecting the edge that is smallest. Okay? In the space below, list the vertices in which they order they're visited. Depth first search is sometimes tricky because depending on the exam, it's looking for visited order or finished order. Visited order is when you first enter a node's quote unquote room, if you think of it like a maze, and finished order is when you are backtracking to your initial spot. And the point of depth first search or depth first traversal, if your search is I'm searching the entire graph to see where I can go, then basically you're going to backtrack to the beginning at the very and when you're done. So, but this one is easy. We're just simply getting to nodes as we see them. So C, this one is super easy. We don't even have to write down anything to figure out where we are. So next one, C. We need to go to what place next? Well, we've got two choices. C has three choices. You have a 5, a 22, and a 30, right? So we select the smallest node first, so we're going to go to B. Our answer will also let us know, will also double as we've already visited this list, or our visited set. So now we're over here. So we're at B currently. B has 1, 2, 3, 4, 5 neighbors, right? B's got 5 separate connections. We're not going to, now technically the shortest is C, but we're not going to get a continual loop of going B to C to B, B to C, because we have already been to C. We don't want to revisit it. Otherwise, we get nowhere. So since C is already in our answer, we're not going to consider that edge. So our weights are 18, 20, 17, and 13. 13 is the smallest, which goes to A. A has 2 edges, 13 and 10. 10 is the smallest, so we go to D. So we go to C. So our path so far is C bad. Okay. D has has 2 connections, but they're to places we've already seen. So we backtrack to A. So we backtrack from D to A to B, right? Backtrack from D to A. And you might need to write these down as you're going, but honestly, it's not. It's a small graph, right? D to A. A has no new connections to add. So so we backtrack to B, right? Everybody seeing how we're just backtracking over here from places. In programming, we'd be handling this with either an implicit or explicit stack. Implicit if we're using recursion, explicit if we're actually using a physical stack, which is what I prefer. And then, so we're currently at B. B has 5 connections. We visited 3 of them already. So our remaining connections are F and E. 18 is our shortest, so we go to F. We backtrack to B. B goes to E. So then we backtrack. We get to C. C has no new connections, so it's C bad fe. Breadth first search, doing the same thing. Okay? So breadth first search is a bit easier to do because we look at the steps that are 1 away, then 2 away. Once again, we are visiting the smallest edge first, so it would be C. So for this one, it would be C, because C has an edge of, let's do it up here. C. Then we have B, E, F. Those are our 3 nodes. We just need to know which one are we visiting first. We're going to go to B because that's the smallest one. But after we visited B, this is our plan. Right? Let's go ahead and write down a queue over here. Right? The way this would work would we'd have a queue. So we'd put B in our queue first. Then we would do. Let's see. We have C has costs of 5, 22, and 30. So it would be E and F. Okay. Next, we go to the next item in our queue. B. Look at B's neighbors. B's neighbors are basically everybody else in the graph. Okay. So C to B we've already done. B to A we have not done. B to D we've not done. And then B to F is already in the queue. B to E is already in the queue. I did that in order of the smallest edges to the greatest edges. So, and that's actually pretty straightforward. E's, we would go and check E next, but we've already examined all his neighbors. Same with F, and then same with same with A, and same with D. CB. Yeah, Sibafad. Prim's algorithm, that's something this is again where we get the overlap between algorithms class and data structures class. I could have thrown in Prim's algorithm in the end of this class, but I much preferred doing the topological sort because I had a nice, easy homework to use again. And topological sort's pretty cool. Prim's is for making a minimum spanning tree. Oh, look, it's Dijkstra's. What was I saying about needing a Dijkstra's no matter what, right? We are going from D. We're trying to figure out D to E, right? The shortest path from D to E. To figure out the shortest path from D to E, honestly, it's silly. List the order in which they become known. Let's go to the whiteboard, and this is going to be my last, I think, theory problem before I go into Actually, how much time do I have?
You have 10.
Yeah, no, refer back to the previous Dijkstra or any other one because I want to get to programming. Okay. So this is a recursive recursive backtracking with a really knapsack. Oof, interesting. Okay. It's cool, but I don't want to do that here. Okay. So linked lists, head next. What is the value of the expression? Result of that. Write the append. Given a node that appends a character at the end of a singly linked list, where whose first node is represented by the parameter head. Your method should use iteration. Oh, not hard. So first off, if you didn't say that, then all I would do for this one is I would say, I would just simply do this. Give me 1 second. The way I would do this problem, if you didn't say that, would be, come on, let's see, comment all that out. Hey, I've got code now, right? So here we go. And all I would do for this is a single line for this solution, or a couple lines, which is if head dot next equals null. If head dot next is equal to no, head dot next equals new node ch, which is the thing we're adding because we're adding a character. And then the next thing I would do is, otherwise I would do an else otherwise. So here's our if statement, and our else is very simple as well. Our else would be append head dot next comma ch, and I would just do recursively. Otherwise, you do the same thing with current and current.next. While current.next is equal to null, move current ahead. And once we exit that iteration loop, we would then execute this line. Except it would be current.next rather than head. Okay. Suppose we want to improve additional information. So suppose we want to improve the efficiency of our algorithm. What would we need information would we need to maintain about the linked list? Well, in that case, if we wanted to append it to the, let me double check. The nodes are, I would also have to check to make sure that head was not null as well, according to this one. But at the end of a singly linked list. The end of a singly linked list, if we just know the head, this is the only way to do it. If we knew the tail, we could just simply jump straight to the tail and make the new node the tail. That would take this amount of time because that's what linked lists are good at. All right. Suppose we have this. The following Java mat uses recursion to search for a key in a binary search tree where we have a root. If it hits the key, blam. If it does, then great. If it doesn't, it returns null. Rewrite it to use search, and so it uses iteration instead of recursion. Not a fun problem as well. This one's fairly, again, straightforward. The way you do that is you cheat, and remember, recursion is just using an implicit stack, so what are we going to do? We'd use an explicit stack, except we don't have to here, because we don't have to ever backtrack, right? What we do over here is just, again, we'd have a current. We'd have a current equals root, okay? And then we'd have the same questions. If current is null, and then we would have a while current, you know what? I will actually write this one out because I already have this over here. So public e-search. BT node e root. Okay, current is equal to root. Sorry if this is a bit smaller than usual. BT node e current is equal to root. While current is not equal to null, okay? And return, if current becomes null, we're just going to return null, okay? One other thing I'm going to do is I'm going to take this e over here and I'm going to do extends comparable e so that I can just I can do the comparisons, right? So while current is not equal to null, if, and again, search, we're looking for some e item, okay? I believe. Yeah, we're searching for some key, and then we're supposed to return some object. Right? We can set it up, but I'm just, the structure of this, I'm just trying to get the structure very quickly here, okay? If root dot item is equal to the item we are looking for, not root, but if current dot item is equal to the item I'm looking for, return, in this case I would probably do something like current dot value to get that, but I'm just going to return current dot item right now, but it should be current dot value because I just don't want to redo everything I have to do. Else, if current current dot item, let's do item dot compare to current dot item. Technically this should be a dot equals as well. If item dot compare to item is less than 0, so if item should go to the left of this item, then current equals current dot left, right? So here we're just doing the same thing we would normally do with this thing. Let's see. Yeah, dot compare to. Equals 0 when they're the same. Otherwise it's greater, so we would say current is equal to current dot right. Okay, and that's how you do it iteratively, right? Oh, now we're dealing with a good problem. Okay, this one's a nice challenging problem. So write a Java method named mirror. We've actually had this one on a final exam before.
I've taken this one on the last final.
Yeah.
I remember this one.
So take a Java method named mirror that takes a reference to a root node of a binary tree and creates a new node with its own new tree with its own node that is a mirror image. For example, if root is the reference over here to our original node, then this is our answer. This is what we want to generate. Hint, it's much easier when you use recursion.
For the love of God, use recursion. You'd be surprised.
Yep, so what we're going to do over here is for mirror. Right, so notice over here that not only do we have 2 and 3 flip, but also the 2 still has the children's 4 and 5, although it becomes 5 and 4, right? And 5 maintains the fact that he has children as well. So when it comes out to these kind of complicated looking problems, public static, BT node, E, mirror, BT node, E, root. Let's go ahead and, hold on a second. display settings. Let's just make it back to where it was. Much better. There we go, much better. Okay, that looks less squished. Okay. BT node root. BT node. Why doesn't it want? What am I doing wrong? Public static. Oh no, it's not static. Public BT node E. Right, if it was static, if I do this as a static, then what am I doing? Yeah, I want to do it as static, I think, because we have two things. Doesn't matter. Does not matter if it's static or not. Static. E. What's going on here? Final review. This cannot be. Okay. Okay. Fine. I think I know why. I think I have to make it a static class. Yeah, I need to make it a static class. Public static. And that's going to make it this problem doable now. Okay. So by default, do that to squash any issues that we are having. So now let's do this. All right. So we need to create a mirror of our original tree. So let's just start simple. Okay, what's the simplest thing I can think of to create a reflection of? And the answer is nothing, right? Because, so if root equals null, if that is nothing, what am I going to do? I'm going to return null, right? The reflection of nothing is nothing, right? Okay. Otherwise, what if I have something? Okay, if I do have something, what do I need to do? Then let's create a node that is a reflection of me. BT node reflection is equal to new BT node root.item, right? We got to create a new node, right? It's going to be the entire point is creating a completely new tree that is a reflection of this. We're not doing any swapping with pointers. If we had to do swapping with pointers, it gets really messy. So we create a reflection. Okay, great. Now, if I don't have any children, that's pretty easy, right? Then then I just return myself, I'm good. In fact, in general, I should return myself as opposed to null, because if I exist, I should return the reflection of myself. All right, so now the question is, what do I need to do for my children? Okay, for my children, if I am, let's take a look at 1, for example. 1's children are 2 and 3, and so he ends up with 3 and 2. Okay, 3 and 2. So my left becomes my right, and my right becomes my left. Okay, what about the fact that 2's children swap as well? And the answer to that is, the first thing you should think of about recursion is when you think about things down the chain is you should say to yourself, that's not my problem. Okay, so let's go ahead and say, that's not my problem, and see if it works. Because a lot of times that does, especially on these exams. Okay, so let's see. Reflection dot left, we need to create a left node. That should be so let's see, new BT node, this is my first kind of attempt, root dot left, sorry, it shouldn't be my left, my reflection, my right becomes my left becomes my right. Ignore that for right now. Right, ignore that for right now, because I'm about to delete this, because it's wrong, but we need to get to the wrong place to get to the right place. becomes my left, my left becomes my right. So that's great, except that if I'm just simply cloning the item, I'm not cloning anything underneath them. Oh, wait, this is a recursion problem. Where's the recursion happening? Okay. How can I create a clone of my child? Wait a second, creating a reflection creates a clone, right? So, let's go ahead and try this and then think through it. What if we do mirror root.right to create my left. So reflection, move to left, mirror. All right, let's think through this. So, I'm here on 1. I create a mirror image of my left node and make it. My right node to make it my left node, and then create a mirror image of my right node to make it my left node. And I'm calling mirror on it, so they're going to call mirror on their children. So 2 is going to call mirror on 4 and 5, and they're going to do their own thing, but he's going to end up flipping them around. And 5 is going to call mirror on his own children, which is also going to flip them around. This works. This is it. This works. This is all I need. I just need to do root.left, and remember, this becomes the previous one, and the attachment happens here, so we're good. So I get to say, okay, this is the root of a tree or subtree. If my child is null, by the way, what's going to happen? If my right child is null, then I'm going to get a null for my left because of this line. It works. Yeah, these are very simple problems. So it turns out recursion problems, while they're not simple in the solving, they are not that complex in being able to read a solution. Again, they look like magic. Yes.
Yeah, meaning that you're not going to be writing a whole bunch of lines of code by doing recursion. It's usually a lot more simple in implementation. It's just trying to get your brain around the idea of this abstract idea. That's the tough part.
And
how it works.
the other thing is that sometimes you might be dealing with a more complex problem. In those cases, like if you have something that is its own distinct task, like remember how on the exam the is balanced question was split up into a height and is balanced question, right? What we did there was we solved the height first and then we called it. So don't be afraid to do that on your own exams, to basically say, I want to make this thing a function, okay? And do it and make your own side function. Yes?
How much of the exam is like coding?
It's literally 50-50 in terms of the point value, okay? So what is the runtime of the mirror method? The runtime of this is, well, we hit each node and we hit it exactly once, essentially. So it's O of n. Oh, cool, we're at the end. So let's go. So there is another exam that I lost a while ago, but it had really only one question here. It was in C++. And I'm going to go over that question because I remember that one pretty well. Let's see. Yes?
Sorry, last question. Can I answer in Python or in Java?
There's a Java class.
Okay.
At the moment, it's a Java class. In the future, I'm hoping to get to a point in the future where basically it can be Python or Java or any language that you choose.
It's just when we try to grade it, is the reason why is that
I also need,
it's just like depending on like someone's familiar with Java or Python, it's just making sure that we keep things consistent.
Okay. The worst case scenario is if you if you can't do it in Python, can't do it in Java, but you know how to do it in Python. At least you're writing something that looks a lot like pseudocode. Okay. Let's see. Suppose you reverse alphabetical order. Okay, this is actually a pretty good one. Suppose you want to print a binary search tree shown like this one. So it appears in reverse level order, so the nodes of the tree diagram would appear in reverse alphabetical order. You may use a stack, a queue, or both as an auxiliary data structure. Describe an algorithm that would accomplish the task. Okay, limiting myself to a stack and queue, what would I do? You use the queue to do breadth first search. As you traverse through as you quote unquote finish with a node, you add it to the stack. Okay? The queue, so first we want to do breadth first search. Okay, we just simply write the algorithm to do breadth first search, which is to use a queue. As I hit a node with breadth first search, what do? I add its child into the queue. Okay, and then I just simply iterate through the queue while it's not empty. Okay, to make it print in reverse with a stack, what I do is I take the algorithm that I just have to do breadth first search, add a stack into it. When I am done with processing an item from the queue, right? I've done it. I've added its children to the stack, to the queue. I take the item and add that to the stack. And from top to bottom, from the bottom of the stack to the top, I have the order in which I went through the queue. Now that the algorithm is done, I just simply continuously pop off the queue until it's pop off the stack until it's not empty. And now I printed everything in reverse. Pseudocode. I could write the pseudocode, but queues and stacks are pretty powerful tools. I like that one. I haven't seen that one before. I think this is a newer version of his practice exam. Okay. Let's see. Just trying to think of, yeah, okay, yes, definitely want to do this kind of problem. Okay, so what are we going to do here now? So we've got this problem. We are going to, and I'm going to set it up, public. How much time do I have? Not plenty of time. Do. Okay, bear with me. Public static void. Wait, no. What time do we go to?
10:15, so we got 5 minutes.
Public static map string to double. String file name. So the idea here of this problem is given a file which consists of a username, space, amount of time spent in for a login session. What is the average amount of time a user spent logged in? Has spent login? What is the average login time for each user? So you might have, I'll just use single letters for each user right now. You have A spent in this time, and then you might have B spent this amount of time in whatever time units that is. C spent this amount of time logged in. A's next session then occurred. B's next session then occurred. C's, and then A had another login section, and then D had another login session, and then A had another login session, and then you get what I say. It's unordered. It's just a bunch of amount of time they spent for this session. Okay. So I want to find the average amount of time we spent logged in. Okay. So for this, we need to do two things. First off, we need the amount of time spent logged in. So total times is equal to new hash map key username value the amount of time I spent logged in. Let's go ahead and I'll go ahead and do that as a double. Why not? Okay. The answer is going to be a double because it's an average, by the way. So that's why I'm doing double. And then integer. Login count. How many times did they actually log in? Make sense? New hash map. Okay. First thing we need to do is read this file. So how do we do that? We are going to do that with a scanner. Scanner SE is equal to new scanner. New file name. Yes, I know that. We need to add an exception here. I'll just add that over here and not bother dealing with it with a try catch because I want to keep this simple. While scanner dot has next line. Right? While we still have lines to read, string line equals scanner.readLine. This is always the easiest way to do a file reading in Java, at least in my limited experience. Okay, we need a string parts is equal to line.split on spaces, right? Because they're separated by a space, let's assume. Okay, and then we've got our And then we've got our string username is equal to parts 0. And we will go and get our double time is equal to, and we'll do double dot parse double parts 1 to convert this. This is a bit harder than I put on the exam because it involves file reading and having to split it, right? But now we've got our username and our time. So what are we going to do? Well, we have two maps here. We need login count and then dot. So what we need to do is we need to do two things. So like if login count dot contains key username, because that's our key, add a not to it. If it does not contain the username, okay, then we haven't seen this person yet. Otherwise, we have seen this person. Fortunately, we don't need to make two if else blocks, because if it's not in one, it's not in the other. So if we haven't seen it yet, then login count dot put username 1, right? And then we also would do we would do, what was the other one? It would be total times put username and then that would be the time that they spent. Else, we would take this and we'll go ahead and make this a bit, we'll do this a bit nasty. Login count dot get username +1 and total time dot get username plus time. And this works because, yeah, I'm doing what I normally do broken up into two statements into one statement. Normally that's broken up. So that adds up our time, the amount of times I have logged in, and the total amount of time. Why am I tracking both? Because I need both to compute an average. I need the amount of time divided by the number of times you logged in.
And this has been on your second exam, like the specific time, without the file reading thing, so that
Mhm.
means this could be something that could be on.
Yep. Although I have a particular love of what I put on that final exam. So let's go ahead and do string double. So this is the answer now. I'm just going to call it answer, even though it's our average. We're going to return the answer. Yes, I know. And that's going to be a new hash map for string user in login count dot keyset answer dot put user, and then we're going to do total times dot get user divided by num. Sorry, what is it? Login times. Sorry, login count dot get user. And the reason I did doubles over here was so that I wouldn't have to cast from into a double. Because you have to do that because generics don't necessarily automatically do that. Okay. So again, good luck on that final exam. The questions typically I typically do 3 coding questions, although those questions typically have a few parts. Like I know the tree one, I typically have multiple parts to that one. Like a couple like, hey, are you understanding the concept of this question? Then I do have a question that does concern hash tables, which I am very fond of. So I'm going to double check with the other, but generally speaking, go over these exams, review, feel free to review previous semesters, and good luck.